Okay, hello. This is the first lecture for Discrete Math. So welcome. Um, we're going to start with section 2.1. So there's some beginning stuff in chapter 1. You can skip that. You can read it if you want, but we're just going to start with 2.1 with logical form and logical equivalence. Okay. Right. So what this is about is kind of a mechanization of thought. Um, you can kind of take our arguments that we have in everyday life and abstract them and play around with them just in the same way you would play around with algebra. Okay. So it's a mechanization of thought. Okay. We'll begin with arguments. There's a lot of definitions here. I won't get too carried away with the definitions. Obviously, in different contexts, they'll have different names for everything that we're doing, like statements. I've seen them called atoms and stuff like that here. But we'll start with an argument. And what is an argument? Well, an argument will be kind of a sequence of statements and then followed by a conclusion. Okay, so you'll have maybe statement 1, statement 2, and all these statements are called premises or premises. And then it'll be followed by some sort of conclusion. Okay. The arguments that we create are kind of, if you studied them like all day long, you would see that a lot of them have a particular type of form. And that'll be called a logical form of an argument. And we can identify these forms and kind of generalize them using symbols and so on. Okay, so this is section 2, the logical form of an argument. We'll look at an example in the book. So I use the book a lot. You may want to have your book by your side or whatever. So example 2, so the argument here, if Jane is a math major or Jane is a computer science major, then Jane will take math 150. Okay, so that's the first statement. If Jane is a math major or Jane is a computer science major, just put CS major, then Jane will take math 150. Okay, so that's our first statement. The second statement then, Jane is a computer science major. And then our conclusion, therefore Jane will take math 150. Okay, so there are statements, and even within the statements, so for example, this first statement, there's multiple statements and they're joined by connectors. Okay, so a connector here, or then, if then, you could consider that as kind of a connector of statements. But we could make it more abstract, right? And then just work with variables like we did in algebra. So how would that work? Let's say P is, we'll call this statement variable. Let's say P represents the statement Jane is a math major. And then let's say Q represents the statement Jane is a computer science major. And then we'll let R equal the statement Jane takes Math 150. We can eliminate all the extra words, and in English there's always more than one way to say something, and we want to simplify these arguments. We want to remove the ambiguity so we can kind of almost program it, right? So so let's see how we could rewrite it with statement variables. We could say if Jane is a math major, so if P or Jane is a CS major, so if P or Q, then Jane is a computer science major, so if P or Q, then if P or Q, then Jane will take Math 150. So if P or Q, then R. Right, so that would be the first statement translated into variables, so it becomes more algebraic. The second statement, Jane is a computer science major, so that's just Q. So 1 and then 2 is just the statement Q. And then finally our conclusion, therefore, and we can use these 3 dots for therefore if you want, Jane will take Math 150, so therefore R. Okay. Okay, so this is a way of abstracting an argument form, and then the book notes in the example that we can have another argument which is basically the same thing, the same type of argument. So let's look at the other part here. If logic, sorry, I went off the screen there for you. If logic is easy or blank, then blank. Okay. So the deal is, if we can identify the form, we're going to be able to put things in these blanks. And this first statement has that if P or Q, if P, so this would be our P, or Q, then R. Right? Okay, so that's the first statement given in the example. The next statement says, I will study hard. And then the conclusion, therefore, I will get an A in the class. Sorry, if I keep going off the screen, I apologize. And therefore, I will get so we should be able to kind of use this first argument as a template and identify all the bits and pieces, and then we'll be able to fill in the blanks, right? So it definitely has that form. If P or Q, then R, and then what was the next statement? So the next statement is Q, and then the conclusion is R. Okay, so if we can kind of identify those bits and pieces in here, we can fill in the blanks, right? So this is our statement, or our argument, right? The form of our argument. Okay, so let's take a look. The second statement should be Q. So this Q thing, I will study hard, must go into this blank. Right? So if logic is easy or I study hard, then R. So what is R? R is this conclusion part right here. I will get an A in the class. Right? So we can fill in the blanks. There's no real thinking involved. This is not critical thinking. This is just basic substitutions, which is how, if you're going to write a computer program that can think for you, which is what they wanted to do at the beginning of the century. They were like, oh, we have all these kind of algebraic systems of where you have axioms, and if you can take the axioms like statements and then plug them into a computer, the computer can do all the thinking for you and give you every theorem in the universe, right? That was the idea. And it seems like a reasonable thing. In my opinion, and this is probably controversial, I don't think humans are all that good at thinking. it would be better to leave it in the hands of computers. And it's a scary thought for some people that our decisions should be handled not by humans but rather by computers. And the computers get rid of all the emotion. It gets rid of all the nonsense. So you have something you're thinking about. You just hopefully someday put it in the computer, and the computer tell you what you should do. Okay, that's my opinion of how to approach this kind of stuff. It's the ultimate, this is what you should do kind of thing. And I guess the more math I did, the less computational it became, the more thought kind of structured it became with proofs. So if you've ever taken like calculus, and there's all kinds of proofs to their theorems, and I'm not talking like your trigonometric proofs. So trigonometric proofs where you're proving identities are fairly simple. You can consider those like simple type proofs, but I'm thinking thought proofs, like I can't think of one off the top of my head, but proving the extreme value theorem or something like that. This takes a bit of thought. It's not just about chaining together identities and so that sort of thing. Okay, so anyways, that would be kind of the idea at the beginning of the century. They wanted to create airtight systems for thinking, which would lead to new theorems in math. Okay, so I'll just shut up before I ramble on too much. Let's get back to the book. Okay, so arguments have statements. So what exactly are statements? And the book goes a little bit, it's kind of like in reverse order. So she introduces the arguments first, and then she starts talking about the bits and pieces. And one of those bits and pieces is the statement. And some settings, they call those atoms. The book also calls them propositions. So what is a statement? A statement is a sentence that is both that is true or false, but not both. Okay? So it's a sentence, or a sentence that is true or false, but not both. Okay? And if you study like set theory, which is always a good thing, that's we're talking about, we wanted to avoid paradoxical statements like the set of all sets that contain themselves contain itself, and that sort of thing. Anyways, let's take a look at some simple statements here. This is problem 5 from the book. The statement 1000, is this a statement at all? So 1024 is the smallest 4-digit number that's a perfect square. Okay, this is something we can figure out if it's true or false, regardless of whether it is true or false. I'm not going to bother figuring that out. It's just, it seems like it is either true or false. It's not going to be both, so this is a statement. Okay. Part B, she is a mathematics major. Okay, this may be true or false, but it's dependent on who she is, right? So right now we don't know, so this is not a statement. It's more like a variable statement. Okay? So not a statement, because we don't know if it's true or false until you tell us who she is. Okay? So anything that has a variable in it like that is not going to be a statement. Let's look at part C, 128 equals 2 to the 6. So this is something we can figure out if it's true or false, so it is a statement. Part D then, it says x equals 2 to the 6. So this is not a statement because you don't know what x is supposed to be, so not a statement. Okay, so pretty simple. Okay, let's move on to more complicated statements. You can make more complicated statements via connecting them together. Okay, so compound statements. So in the first example we were looking at in our notes, example 2.11, that first statement is a compound statement. You see it has this word or in there. That's one of our connectors, which we're going to call the disjunction, okay, later on. Yeah, this is more complicated because it has several statements in it. So compound statements. We're going to use statement variables. So one thing, there's a couple other definitions in here. So statement variables. Those are those P's and Q's and things that, like in this example, when I replace the statement with a P or a Q, the P's and Q's are the statement variables. So I'll just write like P's and Q's and R's. Okay. Then statement form is, so I guess you could think of this as a more generalized version of a compound statement. And it's just I don't know, it's a bag of expressions and statements and logical connectors, okay? So it's an expression of statements, variables, statement variables, or you're just going to have statement variables instead of the statement. So let's just say it's an expression with statement variables, sorry, and logical connectives. Okay, so logical connectives will be like those words and, or, if then, things like that. And in particular, we want to give those things names. Okay, so we'll just start with the not, which is the negation, the and the or, so the connectors to make these compound statements, and then later these statement forms. The connectors are what? Well, we have this tilde thing, that's for not, and sometimes you'll see it in other forms and computer literature and that sort of thing. There's the and then there's the or. Okay, so these symbols, the caret and the upside down caret, or a V is for or, this is for and, this is for not. There's going to be an order of operations, and the the not symbol usually comes first unless there's some parentheses involved. Okay. Some technicality, we're always going to be, if you took like a formal logic course, you'd be do a lot of translations from English into symbols. I was just watching Rick and Morty the other day, and Rick comes out and says, "Oh, you're still studying English. You must be an idiot because that's the language you speak," or something like that. And I'm like, "Oh my gosh, really?" In order to kind of mechanize thought, you're going to need to be able to translate all of English, which is our thinking language, or whatever language you think in, into symbols that can be handled by a computer, right? So you study English so that you know how to translate English and thought into symbols. So it's really an important thing. And with that in regards, there's, like I said earlier, there's a lot of different ways to say the same thing. Okay, so we need to be aware of that. For example, P and Q. I am old and I am over 40. So a statement like a compound statement like that, P and Q. There's other ways to say that in English. P but Q is exactly the same thing. These are equivalent type statements. So this word but and this word and mean the same thing. Okay, so that's the kind of ambiguity you're dealing with when you make translations from English into this new world of logic. Okay, so you need to be aware of that. They come up every once in a while. I try to avoid it at all costs, but you know, you'll be translating, or at least I used to translate things from English into logic all the time when I was reading math. And sometimes it's hard because they use words like but instead of and you know. Okay, so anyways, that's one to be aware of. Another one to be aware of is this neither nor thing. So neither P nor Q. Okay, so the way that one works is it translates as not P and not Q. Okay, so it seems like it should have an or in there maybe or something, but it's not. It's not P and not Q. So this one, the first one symbolically should be P and Q, and the second one using symbols, not P and not Q. Okay. Okay. Sure. Let's move on and maybe look at some kind of problems you'll be seeing in the homework on WebAssign. So doing more examples from the book. So here's example 2.1.2. We want to translate into symbols. And part A, it says, it is not hot, but it is sunny. It is not hot, but it is sunny. Okay. So we can assign statement variables to the phrase, it is not hot. Let's call that P. Okay. And then for the statement, it is sunny, let's call that Q. And then we have our connector. The word but is the same as the word and, so we have P and Q. Okay. For B, it is neither hot nor sunny. Right, so that was one of our weird, how do I translate this from English into symbols? And it's just this right here, right? So neither hot, so that would be not P, nor sunny, so and not Q. Or if you want to use different statement variables, I think the book uses H and S. You can use whatever you want to help you remember what the statement represents. Okay. Okay. One that they like to play around with are inequalities. So first note that x less than or equal to a is the same as x less than a, or x is equal to a. So it's really two statements. It's a compound statement. Okay. Then secondly, this statement, a less than or equal to x less than or equal to b, you can rewrite firstly as a less than or equal to x and x less than or equal to b. But then you could even go further if you want to split that up more and say that these guys are themselves compound statements with ors, right? So this would be the same as a less than x, or a equal to x, and x less than b, or x equal to b. And then to indicate kind of a order of operations, you would probably want to use parentheses on those. Okay, so anyways, let's look at an example where they play around with this idea, and I believe they just want you to do kind of a translation into statement variables. So example 2.1.3, they say let the statement P be 0 less than x, and just so I'm going to use that symbol to say this statement is defined as. Okay, let's let Q be the statement x less than 3. Let R be the statement x equals 3. Okay, and then they want you to rewrite these following expressions in terms of our logical statements. Okay, so x less than or equal to 3. So x less than 3, I mean, this is equivalent to x less than 3 or x equals 3, right? So x less than 3 is Q, or x equals 3 is R. And then if you want to completely symbolize it, get rid of the English, which is kind of a scourge, Q or R. Okay. Let's look at another one. 0 less than x less than 3. Okay. So this is the and version. So this means 0 less than x and x less than 3. And then we could replace these guys with these variables. So 0 less than x is p, and x less than 3 is q. So we have p and q in our symbol version. Okay, one more. C, 0 less than x less than or equal to 3. So what do we have there? 0 is less than x, and x is less than or equal to 3. Okay. So 0 less than x is just p, and x less than or equal to 3 we can rewrite as x less than 3 or x equals 3. Okay. And so we have p and we're going to put this in parentheses to indicate sort of an order. These are grouped together. So x less than 3 is q, or x equals 3 is r. And then let's get rid of the ors and the ands. So this is p and q or r. Okay. So the statement's getting a little more complicated. All right. Now we're going to talk about assigning truth values to these statements. So you can have an argument form, for example, that argument we saw in the middle, which is completely, it follows the rules basically. But if the premises are incorrect, your conclusion will not follow. You need the premises to be true. Okay? So we spend a lot of time looking at truth values, and this is also going to lead into the idea of manipulating statements kind of algebraically. So you could take one statement and simplify it the same way maybe you would simplify an algebraic expression or an algebraic equation or something like that. Okay. So anyways, let's take a look here and see what we're dealing with. Truth values. And we'll begin with the negation, which is the not thing that we were talking about earlier. And we do a table. So here's our statement. Our statement, it's possible that could be either true or false. Okay. So you think of I am alive or I am dead. That's either true or false. And then the negation of p will just flip the truth value. So if it's true, then not p will be false. And if p is false, then not p will be true. Okay. Really simple. Let's look at the and, which we'll call a conjunction. And. Okay. So for example, p and q, which of course we symbolize p and q. This will be true when both p and q are true, and otherwise it's false. Otherwise, yeah. So let's look at the table. We have p, q, and then we'll consider p and q. And we want to look at every variation of truth value for p and q. So you can have true, true, you can have true, false, you can have false, true, and you can have false, false, right? And the typical way you're going to write up your table is just go true, true, false, false, and then make this guy go true, false, true, false. Okay, and that's just, I mean, there's other ways you could order it, but traditionally this is how we order it. Okay, and then P and Q is going to be true when they're both true, but false otherwise. The final one we'll look at for now will then be the disjunction, which is or. And for this, for our studies, this will be true when one or the other statement or both are true. So if P is true or Q is true or both P and Q are true. Okay? So doing a table for that, and this is of course symbolized P or Q. Okay, let's do a table. So P, Q, and to get every variation of trues and falses, we just go true, true, false, false. And then true, false, true, false. And then we want the truth value for P or Q. Right? So it's true when they're both true. Anytime you see a true over here in the row, it's automatically going to output true. So the only time it's false is when both statements are false. Okay, okay, so now let's look at some more complicated versions. So statement forms, so these will be expressions that have statement variables and then connectives. So now truth tables for more general versions. I think we're in section 6. And in your My Math Lab, this will be the most time-consuming part. So you're going through, and you can't write your truth table into the computer. So you have to it'll have like a toggle, an arrow switch. You click the arrow, and it'll pop up true or false, and then you highlight the one that's true, and you have to go through and do these tables. But example, let's take a look at neither our friend, neither P nor Q. So when we translate that statement into symbols, it'll be not P and not Q. And we want to find the truth value of that statement. So we go with P and Q there. And I'll do it the way My Math Lab usually sets it up, or WebAssign, we're using WebAssign. So they'll kind of build up to the truth value by looking at the components or the atomic features of the statement, I guess. And then they'll look at the final statement at the end. Okay. Usually in practice, when I'm doing it on my own, I won't do it like this, but I'll show you how I do it here later, though. So true, true, false, false, true, false, true, false. And then not P is false, false, true, true. And then not Q, you just negate all of these, so it'd be false, true, false, true. And you kind of have to memorize how these work. It's pretty simple. There's not too much to remember. Finally, then, we're looking at the conjunction of not P and not Q. So you're comparing these truth values, and the conjunction says that it'll be true only when both are true. So this should be the only one that's true here. Okay, the other ones will all be false. Okay, and when we talk about truth value of statement, it's this column that we're talking about. So this is the truth value. Okay. So false, 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 true. Let's look at another one. This one has more than 2 statements. It's really not that big of a deal. It's just now you need an extra variable, and to make sure you have all the different true false combinations, you basically need more T's and F's. Okay, so this time we want the truth value of P and Q, or not R. Okay, so we're going to need P, Q, R. And the traditional way of doing this is to go 4 trues and then 4 falses, and then 2 trues, 2 false, 2 true, 2 false, etc. And then this one you'll alternate true, false, true, false, true, false, true, false. Okay. You should have the number of rows is always 2 to the number of statements you have. So before, if you have 2 statements, it's 2 to the 2, so you have 4 rows. If you have 3 statements, it'll be 2 cubed, so you'll have 8 rows. Okay, so true, 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 and then 4 falses. This guy will go true, true, false, false. And then you just let this guy alternate true, false, true, false. Okay. And then we want to start building the statement that we're working with bit by bit. So I need a P or a Q, so I need this half. I also need the not R half, and then I need to compare those two together. Okay? So I'm going to do a row for this half. So P and Q. Then I'm going to do a row for this half, or sorry, a column for that half, sorry. And then I'll do a column for both together. And I usually in WebAssign they set up all the titles for you, but if I did it like a take-home test, I'd expect you to be able to do the whole table on your own. All right, so first P and Q, so I'm going through looking at the first two columns, and it's only true when they're both true. So this is true, and then the rest will be false, right? So if you see a false, it's automatically going to go false. Okay, not R is just taking the R column and flipping. So this would be false, true, all the way through. And then finally, we're comparing this guy and this guy with a disjunction. So if either one is true, it's true. So as soon as you see a true, you know it's true. This one is false. Then this one's true. This one's false, true, false, and then finally true again. And there's our truth value. Okay, when two logical statements have the same truth value, they're considered equivalent. So you can basically, it's like an identity type thing, like sine squared theta is equal to 1 minus cosine squared theta. You can do a replacement, and that's how like a thinking machine would kind of approach some of these problems. You would do substitutions. Given that two logical statements were the same, you can kind of replace them with other statements. Okay. So in particular, I think it's called the Logic Theorists is one of the first kind of thinking programs, artificial intelligence thinking, which is all based off of basic logic. And I can try to remember to give you a link to that. Called the Logic Theorists. Okay. It was one of the first computer programs that would do thinking based off of these logical. Because I mean, with problem solving, a lot of people will tell you, well, you just have to kind of have a feel for it or something. No, I'm not that kind of person. I believe that everything can be kind of programmed and put into computers and done that way. And that's what the logic theorist was kind of going after. They were hoping they could get a computer to do these tasks that were thought to be undoable by computers, right? Like they never thought a computer could play chess, but here we are. So anyways, that's maybe I'll make that like an extra credit thing later on, working with that paper. So yeah, so logical equivalences. This will allow us to do kind of a quasi-algebra type spiel with these logic statements, logical equivalence. As a statement forms that have the same truth value. Okay, so the first one is one of the most important ones we'll look at, De Morgan's law. So there's a table in the book for that's one of the theorems at the end of this section that lists out all the different laws that you need for equivalencies. De Morgan's is one of them, and basically it's kind of like a distribution of a negative sign. So if you have the negation of P and Q, that's going to be logically equivalent, and we'll use a triple kind of equal sign to designate logical equivalence. So it's the same as kind of distributing this guy, and what will happen is it flips the conjunction. Okay, so this will be not P or not Q. Okay. Likewise, we could do the same thing with a disjunction. And it's kind of like not P, so it negates P, and then flips the connector, and then not Q. right? Okay, we want to prove one of these. We'll prove the second one, the second version here, using a truth table. Okay? So we're going to prove logical equivalence by showing that the truth value of this is the same as the truth value of this. Okay, so we have, what is our statement again? It's this one, not P or Q is equivalent to not P and not Q. Okay? So I'm going to have a big, long table. So here's my P and my Q. Then I want the little pieces. I need to consider not P for this part, and then not Q for this part. What else do I need? I need this part, and then the negation of it. So P or Q. And then the negation of P or Q. And then finally, this thing, right? So not P and not Q. And then I need to compare these truth values to say that this thing and this thing are the same, right? Okay, and I'll show you kind of my shorthand version of attacking these problems here in a second. So writing it out like this kind of takes a bit of it's an art of itself, right? But you don't have to go through this busyness. Okay, so anyways, this is kind of how it'll be set up in the computer, though, when you do your homework. Okay, so true, true, false, false. This is true, false, true, false. Negate P, so that's false, false, true, true. Negate Q, that's false, true, false, true. P or Q, so you're comparing these. It's only true, it's only false when they're both false, right? So the last one is a false, the rest are true. The negation of this statement, then you just flip the signs of these. So that'd be false, 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 true. And then not P and not Q, you're comparing these two columns. And it's only going to be true when they're both true. Okay? So that's only true in the last column, or sorry, the last row. So the rest of them are false. Okay? And then we compare the truth values, and certainly, yeah, okay, I get it. These guys are the same, so therefore they are logically equivalent. Okay. How would I do this in more of a sort of a general way? How would I set it up? So in general, in practice, I wouldn't do this piece-by-piece version of the table. I would just kind of do it like this. Or Q, and then the other side, not P and not Q. So you have true, true, false, false, true, false, true, false. And I start on the inside, so you kind of do an order operation. Start on the inside first, so P or Q, that's going to be true, 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 false. And then I negate it, right? So then I'll just take these and negate them all, and I'll get false, 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 true. And then that'll be the truth value of this side. Okay? And likewise over here, first I need to do not P and do not Q. So this would be false, false, true, true. And the order of operations, negations comes first unless there's a parentheses, right? Okay, and then the not Q part will be false, true, false, true. And then the and is going to give us false, 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 true. So there's the truth value there. And then you compare them. So again, this is just kind of a shorthand way of attacking this problem. If you don't know, if it's not clear to you how to set up this chart, I would recommend just kind of doing it this way. Okay? And the only reason why I even show you this way is because that's what the WebAssign is going to do. Okay. Let's move on. Tautologies and contradictions. When all of these are true or all of these are false, they're considered special. In particular, if they're all false, it's a contradiction. If they're all true, it's a tautology. And there's simple facts in life where you can kind of think of it as a tautology. For example, I am either dead or I'm alive. So P or not P. that is a tautology. Either one or the other is going to be true, right? On the contradiction side, then I am both dead and alive, right? So in that case, that would be a contradiction because you can't have both the same, both being true at the same time. So tautology and contradiction. So the truth value in these cases, for a tautology, it's always true, and for a contradiction, it's always false. All right? Do a little chart there. All right, so let's take a look at that example I was just talking about. And it's a good place to start out with a proof if you're doing a case-by-case proof. You know, it's either going to be true or it's going to be false. So you investigate both cases and see what happens. So it's either true or it's false, right? So if you do your truth table, you have P, then you have not P, and then we have P or not P. Okay, so for P, it's either true or false. Not P is then false or true. P or not P, it's always going to be true. Okay, so long as one of them true, it's always true. And if you have all truths, the truth value tells you it's a tautology. Okay, so pretty easy one. The book will give you much harder problems to attack. Let's look at one that's harder now. So like number 40, we have P and Q, or not P, or P and not Q. Okay. So our truth table, P, Q, and then I'm going to do it kind of the shorthand way like I was showing you earlier. So P and Q, I have to kind of do that one, and then I also have to work with not P or P and not Q. Okay. Alrighty then. So P, true, true, false, false. Q is true, false, true, false. Over here then, I'm working on these two sides kind of separate. The truth value of the entire expression is going to be right under this 4. Okay, so order of operations kind of have to do these guys separate and then compare their truth values. Okay, so let's do this side first. P and Q is true only when they're both true. Okay, and then over here, you have to do negations first and also parentheses. So you work with the inner parentheses just like you do in arithmetic. So inside here, in this innermost parentheses, you see there's a negation. So you have to do the negation first. So I'm negating Q. So I'll have false, true, and then I compare that with P. So P is true, true, false, false, and the comparison is the conjunction. So that'll only be true when they're both true. So this is false, true, false, false. Okay? And that's kind of that part. Then over here, I have to do a negation on P. So that'll be false, false, true, true. And then I'm comparing this column with this column using the disjunction. Okay, and that'll be true when either one is true. So this is false, true, true, true. And then I'm comparing this and this, and that goes right there. Okay, so you're comparing it with a disjunction, so this will be true, and then this is true, and then this is true, and this is true. They're all true, so therefore it's a tautology. Okay? Okay. Using De Morgan's, now we're talking about more kind of translating English statements and working with those. This example from the book example 2.1.9, and they work a lot with those, well, not a lot, but they work sometimes with inequalities because we want to apply logic to mathematics. And of course, some colleges have mathematical logic courses, which if you're really interested and you're going to be doing a lot of pure math, you probably want to take. We don't offer that. I don't think Cleveland State offers it. But anyways, note some things, some factoids about these inequalities. So there's 4 basic types of inequalities. So we can rewrite these as kind of negations. X greater than or equal to 2 is the same as saying that x is not less than 2. Okay. X less than or equal to 2 is the same as x as not greater than 2. And then saying x is greater than 2 is the same as x is not less than or equal to 2. And then x less than 2 is the same as x is not greater than or equal to 2. Okay? So when we go through and negate statements, we can kind of work with either or, right? If you want to work at this side, work with that. If you want to work with that, work with that. Okay, so we want to write some negations. Let's take a look at the example that we're going to be dealing with. John is 6 feet tall and he weighs at least 200 pounds. So John is 6 feet tall and weighs at least 200 pounds. Okay, okay, we want to negate this statement. And so how would we write that? So instead of saying John is 6 feet tall, it'll be John is not 6 feet tall. And this is De Morgan's rules, right? So to negate an and statement, I'll turn it into an or statement. So John is not 6 feet tall, or to negate weighs at least 200 pounds. You can consider these statements up here. So weigh at least 200 is the same as saying that John is greater than or equal to 2, which is the same as x not less than 2. But if you negate this statement, they kind of undo each other, right? So saying that it's not the case that x is not less than 2 is the same as saying that x is less than 2. So it just magically erases the not part of it. So or John, in this case, weighs less than 200 pounds. All right. Okay. So symbolically, John being 6 feet tall. I don't know how we're going to do. John is 6 feet. This part of it is kind of maybe the confusing part. Weighs at least 200 pounds. It's kind of like saying x is greater than or equal to 200, right? And then we said above that equivalently is the same as x is not less than 200. And then to negate this statement, you're basically saying, so to negate x not less than 200 is the same as saying x is less than 200. Okay. So saying that John weighs at least 200 pounds, negating that statement is the same as saying that John is actually weighing less than 200 pounds. It's probably easier just to think of it without all the symbols and stuff, and just think of it as you would in English. Anyways, let's look at another one. 2.1.10, we want to negate the statement -1 less than x less than or equal to 4. Okay. Okay. So let's go through and do this. This is an and statement, right? So from before, it's the same as writing -1 is less than x and x is less than or equal to 4. And then to negate this, you need De Morgan's rule. So to change the and into an or, and then saying x is greater than -1, that's equivalent to saying x is not less than or equal to -1, and then if you negate that, you get x is less than or equal to -1. And on this side, x less than or equal to 4, negating that is basically just saying x is greater than 4. It's kind of a complement type idea if you can think of it that way, right? So visually, and they do this in the book as well, x less than or equal to 4, if you put that on the number line, here's 4, x less than or equal to 4 would be all this stuff here. So to negate that kind of interval, you take the complement of it, and what you're going to end up with is this interval over here from 4 to infinity, right? Which is basically just saying x is greater than 4. Okay. All right, so hopefully that makes some sense. It's okay. So the last section here is kind of let's not use the truth tables anymore for logical equivalence. We're just going to have these guys memorized. So I think this is section 9 in my notes. It's a summary of logical equivalencies. Okay, and this is located on page 49. It's theorem 2.1.1, so it's this chart. Generally, I would have, if this was a normal class, I would have you memorize these. You should be familiar with them. I'll have a midterm and WebAssign, and they kind of expect you to have the main ones kind of memorized. Usually, though, I have them memorized. You could do like note cards with them, and some of them are kind of obvious, right? So you're familiar with a lot of these from basic algebra and arithmetic. So like the commutative law is similar to 1 plus 2 equals 2 plus 1, right? So here P and Q is the same as Q and P. And yeah, so on and so forth. Okay, so we can use these to simplify statements and make logical equivalences. So let's look at example 2.1.14, and we want to verify. Okay, so verify that this statement form is just plain old equivalent to P. Okay, so you know, it's very powerful, this logic stuff. It cuts through the nonsense. Okay. All right, so we'll start on the more complicated side, and it works a lot like a trig type proof. Okay, you move from one side to the other side. Okay, so we'll start over here, not P and Q, and P or Q, and then we tried to get to P using our table, that theorem 2.1.1 with the logical equivalencies. Okay, it may take some practice to get used to this, and there's not a lot of homework problems with this, but some things you could do. Okay, all I know right now is De Morgan's, right? So you could do De Morgan's here. You can basically distribute, quote unquote, distribute. There's a, be careful, there is, distribute means something else in this context. So just be careful about what words you choose. So anyways, when I do De Morgan's here, I'll have not P and not Q, right? And P or Q. And whenever you do a step like that, you need to tell me which theorem or which equivalence you used. And this equivalence was De Morgan's. Okay, so De Morgan's. Okay, and then we can simplify this not P. Okay, so not P is going to be the same as, you know, if the book bothers with that, yeah, double negative law. So not P is the same as P. So P and not Q. And you really can't take anything for granted at this point, right? It's kind of like you're working with one arm tied behind your back. You know that not P is probably P, or maybe you don't, maybe you do. But there's things that you sort of take for granted in arithmetic, like 1 plus 2 is the same as 2 plus 1. And when we're working here in the beginnings, you kind of have to state, oh, that's the commutative law. Okay, you can't just, because I learned it in elementary school, I'm not going to, no, you have to record why you're doing it. So this was the double negation law, or the double negative law. Then I could kind of see that there's this P and a P over here. I think I screwed up something. Oh yeah, when I did De Morgan's, I have to flip this. Sorry about that. Now here's the distribution part. So distribution is really more like this. It's if you have P or P, Q, or Q and R, something like this. The distribution is this. So it goes P or Q and P or R. That's what they mean by distribution in this context. Okay, and you can also go in the reverse direction. Okay, so when you see it with P or, you could kind of do a reverse distribution. You could say P or not Q and Q. Okay, so this was the distribution. Then this not Q and Q, that's one of those contradiction type things, right? You can't have it both ways. I can't be alive and dead, right? So we can simplify that, but in order to simplify it, we need to do it, put it in the exact form that we would use it in our table. Okay, so this is what we want to get at. We want something like this, right? But it's this one we want. P and not P is equivalent to a contradiction. So in order to get in this form, I got to use the commutative law. It's one of those things. It seems like, oh, those are equivalent, but it's because you've had it beaten into your head by elementary schools. So I have to go, just painstakingly, slowly. So this is the commutative law. And then you can apply I think it's the negation law. Yeah, so this would be P or a contradiction where Q and not Q is equivalent to a contradiction because of the identity, or sorry, it's the negation law. Okay. And then we could use the identity law. P or C is the same as P from the identity. And we've proven the logical equivalence without having to do the big truth table, okay? And it's much easier to work that way. And you'll see it has that sort of algebraic form. It's like doing algebra. And it's not that far of a leap of faith to say, oh, I can use algebra to do thinking. And I could think quicker than maybe somebody who's fiddling around with some argument, and I don't know, it's a powerful thing, like I said, and it leads me to believe that computers will just be way better at doing decisions and thinking than humans. And our sort of, people think that we're so smart. I don't think so. I don't know. No, computers can do this kind of thing better than we can. And you see it even in society today, I believe. I don't know. That's my opinion, and I think it's really interesting stuff. We'll continue on with this more and more. It'll allow us to basically symbolize any argument we want to, and just work with the symbols and push the symbols around and do kind of algebra on them. It's really cool. So, anyways, we'll see you next time.